everyone, welcome to the first speaker series hosted by the Mars Robotics Association. We're based in Mars, Pennsylvania and have FIRST robotics teams for grades 4th through 12th. This month we have Ken Neiss, a NASA Research Portfolio Manager for the International Space Station. In that role, he assists payload developers and commercial companies develop investigations and business plans for the International Space Station and walks them through the certifications process for both safety and interfacing with the station. Previously, he served as Commercial Crew Integration Lead working with SpaceX and NASA to work through development and approval of emergency systems for SpaceX Crew Dragon. In addition to a series of technical manager roles, he also worked many years in mission control as a Cronus Specialist Flight Controller in charge of the onboard communications and data systems for the International Space Station, and led various crews and missions, including some with the Space Shuttle. He hails from the suburbs of Philadelphia. After Unionville High School, Ken earned his bachelor and master degrees at Penn State University in the field of electrical engineering and was hired in 2004 by NASA to work at Johnson Space Center in Houston. Outside of NASA, Ken is an avid sports fan, especially the sport of soccer, to which he plays, coaches, and referees. All right, hello everyone, and welcome to Mars for the first ever speaker series hosted by the Mars Robotics Association. Hello, Mr. Neiss. Glad you could join us for tonight. How are you today?
Hi, everybody. I'm doing good. We just took back everything that we put in the garage for the hurricane that luckily missed us, and we put it back out on the patio. And yeah, we've got great weather, so I'm doing pretty good.
Good to hear. All right. So first, Mr. Neiss will explain a bit about what he does, and after, he will answer some questions submitted by the viewers. So click the link in the description below to submit a question. Mr. Neiss, would you like to tell us about yourself and how you got into NASA?
Absolutely. If we can go to the slides, I think it's a great lead-in. So my story begins in Pennsylvania. I'm from outside of Philadelphia, Westchester, Chadds Ford, Unionville area. So I grew up there with my two brothers, older and younger, and I always had an affinity for space. Everything space was just cool to me. As you can see in the picture to the upper right-hand side, you see a little plastic space shuttle with a broken tail. That was my kid's toy when I was growing up, and I tend to break things, so that's why it's missing its tail. And there's some other toys that I've acquired in my adult years. But if you look into the left-hand side, my parents, on a trip to Texas, into Houston area, we stopped off at Johnson Space Center when I was little, or younger, I should say. I'm the middle-sized one in that blurry picture. So I got my first taste of NASA there. And as I grew up, I became pretty good with computers and math and sciences. That's what became my focus area, math and science. Next slide, please. So as I took that, because math and science were easy to me and I really enjoyed it, I went to college at Penn State University. I was in the Penn State marching band, blue band. You can see some of those pictures there, and I enjoyed that. It was a good engineering experience. I did focus on communication systems in electrical engineering. I also did some study abroad in Leeds, England, to get some diversity experience and see how England was to live in. And also you can see that Duquesne University badge. I lived on the campus of Duquesne University when I did an internship in Pittsburgh for one summer 2000, I think. And as I did communication systems, NASA would always come and have a booth at the career fair at Penn State. And so I'd go and visit them freshman, sophomore, junior, senior year, talk to them, give my resumes. And when I decided to stay for grad school, that's when we had some serious conversations and they took an interest in me. And at that point, I knew my foot was in the door, and I had a selection of jobs that I could choose to go to. One would be a literal rocket engineer, rocket scientist at Kennedy Space Center. Another one would have been biomedical engineering at Johnson Space Center. And the one I ended up taking was a communications specialist in electrical engineering working in mission control for the space station at Johnson Space Center. So that's kind of how I got there, just the love of math and sciences. And when I took a site visit, next slide, please. When I took a site visit, it really cemented, this is where I wanted to be. This is just, the cool factor was off the charts. I got to visit Mission Control. I got to visit Apollo Mission Control, where I watched the movie Apollo 13. That kind of brought me back there. And then I got to play in the space shuttle mock-up in the picture into the right-hand side. I just really loved it here. And I realized that this wasn't a normal 9-to-5 job. This would be something I'd want to do, and had a lot of different areas I could explore once I started. And so I knew this was a place for me. So I picked up from Philadelphia and drove across the country and landed in Houston and set up shop here. And I've been here for about 16 years now. Next slide, please. I got the thing I was looking for a long time, that congratulations official message from NASA in 2004. And I started my career was called in the CATO group, Communications and Tracking Officer for the International Space Station. That was a little bonus in the upper right-hand corner. That's me, and I think it's the pilot seat of the space shuttle simulator, enjoying my run there. And one of the jobs is CATO. We got to work during shuttle missions with our counterparts on the shuttle side. We had an integrated mission, and we got to work and tie the communication systems together. So that was a really fun experience. Next slide, please. So that's really how I got my foot in the door. And now I can talk to you a little bit about mission control, because a lot of people have questions about mission control, and it's intriguing. So I'll show some images here of what mission control is and isn't. The main picture is the outside of mission control. It has no windows, and has no windows for a reason. It was built in the time where we wanted to protect our national assets. So they're worried about other countries trying to look in at us and get secrets. So no windows could be had in the building. And recently, I'd say over the past 5 to 10 years, we actually renamed Mission Control the Chris Kraft Mission Control Center after the first flight director, Chris Kraft. And you see in the bottom left-hand corner is the main entrance to Mission Control, the silver doors with lots of security cameras. That's where you badge in, and once you're in there, you're officially in the Mission Control area. You're not in the Mission Control room yet. Next slide, please. So this is an image of the space station, and taken pretty much after assembly complete in 2011. You see the solar arrays, you see European vehicle on the back that is docked there. Or sorry, I should say the European vehicle in the back there, and you see various aspects of the fully built space station. What you can't see is some of the equipment that I've been working on as a CATO. You see some dishes in the middle there. You can actually see a lot more behind me. If you zoomed in this picture in the dead center, you'd see some satellite dishes. Those are the KU band dishes behind me. You'll see S-band communication assets also behind me, UHF systems, and those are all the systems that, as a CATO officer, I'd be in charge of. One of the cool parts of my job was I was in charge of the external cameras on the space station. So when the shuttle did its rendezvous and docking, my video would go to various news outlets live. So I better not screw up, which I may have once or twice, as my brothers never let me live down. But anyways, it was a really cool experience. Next slide, please. What we see now is the current and past crew on the ISS. From the top left is our US astronaut, Chris Cassidy, former Navy SEAL and now astronaut. He's up there with Anatoly Venetian and Ivan Wagner. They're both from Roscosmos, our Russian colleagues. And the bottom two guys just finished their stay Bob Behnken and Doug Hurley. You guys probably saw the media coverage for the SpaceX Demo 2 mission. It was the first mission to demonstrate a crewed vehicle with crew in it, coming to the station, docking, rendezvous and docking autonomously, and then leaving and landing safely in the ocean. They were on the ISS for about 60 days. They did 4 spacewalks, and they proved this vehicle is flight worthy, and it's getting ready for certification. And the next SpaceX with astronauts will be coming to us in the October-November timeframe. Next slide, please. Here's what a Soyuz rocket launch looks like from where they launched from Kazakhstan. Baikonur is what it's called, Baikonur Cosmodrome. The Russian Proton rocket with a Soyuz module attached to the top has been the staple of the Russian space vehicles since the 60s. It's very safe. They upgrade some of the internal avionics, but for the most part, the physical characteristics have not changed. It's actually, until the Demo 2 vehicle and the SpaceX Dragon is fully certified, it is the only space-rated human vehicle. And here's, next slide, please. Next picture is that Soyuz vehicle docked to the ISS. Next slide, please. So here's a picture of what flight control team looks like and what mission control Houston looks like. It's a little bit old with the blue consoles. They recently changed it to brown and black wood grain consoles. We can kind of see the layout of what mission control looks like. You have the 3 large screens in the front. You see various video feeds, external camera feeds on the left monitor. You see what's called the ground track in the middle center monitors. What you can't see in this is on that feed, it shows the track of the ISS and any visiting vehicle over the ground, spread out onto the 2D screen. It also shows the various comm assets, the various satellite links that when the ISS is in range can attach to and link to. It also shows the various ground sites that we can communicate with, and it showcases the sun and some other aspects of what the main characteristics are. And the bottom 2 portions of that monitor are 3D computer graphics of what the space station looks like, the orientation of the solar rays, and so forth. On the right-hand side, you see a caution and warning display. You see on the top is all the commands to the vehicle. Sorry, in the middle area is the commands to the vehicle. The bottom is the caution, warning, and advisories. You'll see a little rectangle in the middle with green. That shows it's got good comm assets for sending commands and for voice. And for the right side is actually orientation of a docking screen, shows where the vehicle is in relation to the station. And on the screen and in the control center, all the different consoles, all the different flight control representatives, flight controllers in the room. So I'll just go right from the top. Flight director would be sitting to the right of the screen. He is the second console. He's got the two men sitting down is what you see in the screen. They're in charge of that whole room. Nothing gets done without their say. And honestly, nothing gets done with the international partners without conferring with the flight director. So they're in charge. They got the final say and what everybody says and what it does in the room. And then the ground controller, or the GC console. They're in the back right. You can't see them in the screen, but they're in charge of all the ground systems, the ground hardware, the telecommunication systems on the ground, and also the TDRS satellite assets. Any problem on the ground, any problem with your console, any problems with satellite linkage or the data networks on the ground, you talk to them. And then the Cronus, that's actually my position. When Cato merged with Odin, Odin is the onboard data interface networks, the computer systems, and the crew's computer panels. We became Cronus. So that we're in charge of the data systems, communication systems, audio, video, cameras, commands, telemetry, everything telecommunications on the ISS. That was that controller. And you can see that person in the second row in the middle. Got a little bald spot there. That would be actually me in that picture. And then moving down, ethos is the environmental control system. They're in charge of making sure the crew is safe, a safe atmosphere to breathe. It's the right temperature, and in charge of the emergency systems and life support systems. Spartan is in control of the onboard power systems and power distribution. They're in charge of the solar arrays and the battery charging and discharging and making sure the station, solar arrays and power is in a good configuration to support both payloads and sustaining the crew. Moving on to Capcom. Capcom's in charge of communicating with astronauts. Sometimes as engineers, we talk a little bit engineering in the weeds speak, and the Capcom console is usually an astronaut, not always, but they're able to translate the weeds talk into their fellow crew members, what they understand based on their training. So they're a good resource to run things by and to interface and to make sure on the ground teams keeping a crew perspective as to what they need to know and how we can help them. Then there's a biomedical engineer. They're in charge of countermeasures and making sure the crew is exercising and has the devices and equipment to do exercising, and they're staying in healthy shape. They work closely with the surgeon, which happens to not be on this chart. The flight surgeon is basically the flight doctor. They talk to the crew, make sure the crew's healthy. They take readings. They get various blood samples and urine and other types of data collection on astronauts to make sure they're healthy and they're a voice to make sure they get enough rest and sleep and so forth. Then there's the EVA console. They're in charge of spacewalks and prepping for spacewalk. They do a lot of training with the crew. They do neutral buoyancy lab runs, which is going into the big pool that they have, about 2-3 stories deep, size of a football field as well. And they run basically water runs in full astronaut outfits. And then the crew members put on weights on their ankles so they can create neutral buoyancy so they can effectively float in the water and test run various spacewalks and using tools on the external of the space station. And then there's the ISO, Inventory Stowage Officer. They're in charge of all the inventory, where things go on the ISS. ISS is big, but it's got limited space. And we tend to fill up all that space with hardware that either is about to be used or has completed its lifetime, and also a lot of trash and foam and stuff that is no longer needed. So they're in charge of making sure we put things in the right place, we make the best use of all the space, and keep the place safe for if the crew ever needed to move around in a hurry. The ICE is Integrated Systems Engineer. They work with visiting vehicles docking to the space station. Once those get to the space station, they work with those parties and partners and make sure that the JSC team and the international partners are all configured and communicating and keep that vehicle in the best configuration it can be. Then there's Ops Plan. They're in charge of planning everything, every minute of the crew day, of every week, every month. They run the show of the plan and making sure we're making the most of the crew time, most efficient use, and we're not overbooking resources. We're not using, too many cameras or, too many minutes a day, or if payloads can't be done together, they're making sure they're catching those constraints and planning things out accordingly. And they work with all the different partners, including the Russians, to make sure we're meeting everyone's expectations and agreements. OSO is kind of the MacGyver of the space station. They will figure out ways to fix anything on board the space station with whatever tools are available. And when they do, they document them so the next time something like that fails, we can use that as a basis. So they have to figure out what types of things could fail and practice them on the ground and practice them with astronauts on the ground and get us ready for the inevitable when something fails on orbit. The Pluto team's in charge of the onboard LAN, I should say, the non-critical systems, but basically the crew internet and the way to communicate from the payloads to a network that we can get that data on the ground for those payloads. So they're very important, and make sure the crew's up and running and can communicate to us, can check their emails, can stay tied into their family, and so that's what they do. The Rio is the Russian integration officer. They're in charge of being our eyes and ears out in Moscow. They will translate and work with our Moscow support group to make sure that the Russian team knows what's going on our side and vice versa. Then there's Robo. And I think given the audience we have right here, the robotics team, this Robo team works the robotic arms. They've got a big arm, the SSRMS, and a small arm, the SPDM. They also had the SRMS, the shuttle robotic manipulator system that they worked. And they're in charge of planning and coordinating and testing and doing computer runs of the multi-pivoting arm that, one arm, one grapple, one end can turn into a grapple, the other one's attached to the base, and it can basically walk on over itself, switch what's the grapple and which is attached to the base. And it can traverse pretty much the entire truss of the ISS, and the little arm attaches to it and can do interesting functions. It can actually perform demo tasks for things like refueling and doing robotic turning of screws out in space. So it's a good test run, but it also gives a little more dexterity onto small, fine movements. Then the topos are in charge of the trajectory and pointing. They make sure that nothing hits us. They work with our other government entities and make sure that there's no conjunctions, nothing to be aware of, nothing that the ISS needs to get out of the way from. Then there's a VVO, the Visiting Vehicle Officer. They work, again, with our partners when those vehicles are rendezvousing or have not yet docked to the station, and they make sure that we're talking to those control teams and they're talking to us, and we're in a good situation, and that vehicle is not in any danger, and the vehicle is not going to endanger the ISS. Another one, it seems I forgot, is ADCO, very important role. They're in charge of attitude, determination, and control. So they're in charge of guidance, navigation, making sure the station is in the correct orientation, is flying the right way and the right attitude at the right speed. And they control the CMGs, the control moment gyros, on the ISS, make sure we don't start tumbling out of control. And they work very closely with our Russian colleagues and help us be able to use the equipment to point at the right satellites at the right time. Then there's Public Affairs Officer, PAO. They're the ones that you hear talking about space launches, or when there's like the demo to SpaceX mission, they'll be telling you the play-by-play of what's going on in mission control while they're there. And that's really the rundown of the flight control team. And sorry it took so long on it, but there's a lot of different people on here with a lot of different backgrounds. And I wanted to touch on this because people always ask, what can I like this specific field, but I don't think I can work at NASA, because NASA, you have to be a certain aerospace engineer, or you have to be an expert on guidance and navigation control. As you can see in these slides, or the slide right here, it's a lot of different tasks, a lot of different backgrounds, even in mission control, even in the flight control room, that work to help on the ISS. And there's even more outside the flight control room. So I wanted to spend some time to touch on these different positions and their backgrounds. Most of them have some engineering background, but they're varying, very different specialties. So I think we can move on to the next slide. So when I got to mission control, when I started Cato, I was the peon. So you have to go in and you finish college and you go into a mission control position, And they say, guess what? You have to learn a whole new way of doing things. You have to learn, basically go back to school. So you spend another couple years in training before you're able to sit in any of these rooms. And if you look at I think the bottom middle one is the back, what's called the back room. When you get you learn your stuff, you take some tests in various integrated simulations, and you get certified in the back room position, which is a helper to the front room. And you work your way up from there. And you do simulations, you get some experience in the back room, and then you work to this front room position, what you saw on the previous slide, and you see a bunch of pictures in this slide. Then you're in charge. You're in charge of that console. You make the decisions. It takes a couple years, 2 or 3 years to learn and get up and pass the various tests to get into this position. But that's when you get the responsibility and you actually have a lot of fun. You do work nights and weekends. Mission control, especially the Kronos position, is 24/7, 365. Currently, they work 3 9-hour shifts throughout the day with a 1-hour overlap. But it's a lot of fun. And you can see my console on the left-hand side and the upper right-hand side, some of the tools we have at our disposal. You see that the far right screen has a bunch of pictures, almost looks like blue eyeballs. And that's actually a representation of what our antennas would see if it was a camera. And it was superimposed onto in a radial coordinates. So I can see when a satellite's coming into view. I can see if we're gonna have good or if we're gonna have some blockage. Middle screen has various indications of the telemetry in front of us. The PC screen, which is directly in front of me and smaller than the rest, is a PC. It shows a timeline of events that the ops planners planned, and I have to go and make sure I'm ready for each one of my activities and get ready to command. And then you see in the upper left-hand corner, that's a flight picture, one of our shuttle mission support, but that's all the various front room and back room positions. Come take a picture. There's a lot of people involved in making these missions successful. And then the center of this collage, you see a hurricane, you see a shuttle almost doing some backflips. Those are some of the video imagery that I took that got put onto TV at various aspects. One is of a hurricane, and one is the shuttle coming to rendezvous and dock doing its backflip to check for tile damage before it comes to dock to the space station. Next slide, please. So we just talked a lot about ISS, different positions in mission control, my experience in mission control. I was there for about 13 years working one or more aspects of mission control. And then I moved on to different roles, including working on the commercial crew program. And seeing that we had this Demo 2 mission, and we've got a Boeing mission coming up at the end of this year, thought I'd touch a little bit on this and the aspects of these vehicles and my experience. So the commercial crew program was put into place to try to quit our reliance on Russian assets for getting into space, to bring back the ability to launch U.S. crew from the U.S. So you see, we have awarded 2 companies, SpaceX and Boeing, the contracts for being the providers, the launch and vehicle providers to our astronauts. So you saw the past couple months, the SpaceX Crew Dragon. It's a really cool vehicle. The Boeing Starliner, it's also going to be very exciting once it's ready. And you see the various astronauts that are allocated for the first couple missions of demoing and doing the crew rotation missions up on top there. So I want to spend some time on the SpaceX Crew Dragon, just a little bit, because I actually worked a little bit with SpaceX as one of my other roles. I was an integration lead for about 6 months to close to a year, I should say. And before that, I worked with them on their communication systems, on the design and what capabilities they needed to have. So SpaceX vehicle and working with SpaceX was a very eye-opening experience. They have a very different way of approaching problems, which is good, because it shows NASA some new aspects on how to think and how to be agile. And it's a mutually beneficial relationship, as we brought to the table our experience and our background in making sure things are safe. So it was a good give and take. I worked with them specifically on their emergency systems, making sure they had the right capabilities. They did the right risk trades and right risk balance that NASA would be amenable for, and that our crew would, in the end, be in control of themselves. They'd be in control of their own destiny. So make sure that that vehicle had the capabilities to both work autonomously, but also the crew can take over manual control in case there's a problem. So it's a really neat vehicle. Working with SpaceX was very cool. Out in LA, I got to visit, and I got to see Elon give a bunch of speeches out there. We got to see how they operate and their production system. I got to go inside the Demo 2 vehicle before it flew. It was a very, very good experience. And it also brought an aspect that I hadn't learned before, which is project and management and systems engineering and the risk trades of the safety involved in going with that. When you work project management and systems engineering, there's pretty much a triangle of what you got to think about. There's the safety and the risks, there's the physical cost, and the schedule. And if you pull on one, those others have to give. So if you're gonna want to make things much safer, then it's going to impact the cost and schedule in some aspect. If you're going to try to reduce cost, then it might impact your safety in the end or your schedule. If you're trying to impact your schedule, if you need to extend your schedule, well, it's going to definitely affect your cost. And vice versa. If you try to accelerate your schedule, you're going to increase your risk. So we got to see a lot of that in play and work with the various reps from both NASA and SpaceX to come to a happy medium of where we wanted to be. So that was a very exciting and eye-opening experience. Next slide, please. And here's some more images of the SpaceX. So you see the vehicle, you see the first Demo 2 crew taking the walk into the vehicle from the walkway and Launch Control Center in KSC. You see KSC on the far right, the vehicle vertical assembly building, and you see the crew working the controls, the touchscreen controls in the vehicle. And that was also, the touchscreen was an aspect where I got to test out and give feedback along with the crew when we were developing those screens. So that was a good experience. And the upper right-hand side, you see the Hawthorne, California headquarters of SpaceX. You see one of the returned Falcon 9 rockets that they put out on display. Next slide, please. So after I did my fun at working with NASA and commercial crew and SpaceX and a little bit of Boeing, I've moved on to a new role. And I just want to tell you a little bit about this because it's a big aspect of what we're doing right now with the space station itself. I moved into research integration. My title is Research Portfolio Manager, which means I'm the NASA liaison to various payloads, various projects, and other space agencies projects and payloads. And this collage, it might be hard to see, but I'll try to go through each, these pictures very, very high level, because each picture represents one of the payloads and investigations I've worked on personally. The first one is upper left. I'll start from the upper left. If anyone has an Apple TV, especially the 4K TV, you'll notice that after it goes to sleep, it goes into slideshow mode. NASA worked with Apple to have the crew take a whole bunch of 4K videos and imagery, and that was one of the payloads that I was leading. And that imagery turned into all those screensavers, 4K screensavers that you see on your Apple 4K TV. It was very tough to schedule and to work the details of it, but it turned out to be really cool. The next one is Hermes. It's a regolith investigation. It simulates regolith, small fine particles that the top layer of soil on the moon and on asteroids, and how we'd be able to if we have an asteroid or another moon mission, how best to work with that type of dust. Are we going to be able to attach to it? Are we going to have to worry about the dust getting into our suits or equipment? So that shows how the dust and the fine particles interact with the smaller and larger bodies in zero gravity, or sorry, in microgravity, but with zero pressure because it's at a vacuum. The one underneath that is a Canadian investigation I worked with called Bioanalyzer. And right now, with the crew takes a bunch of blood samples almost daily and other samples, and they freeze it and they send it to the ground when they get a chance to analyze how the microgravity, extended microgravity affects their body from one point in their time to the next. This investigation and payload have them take a little bit of that blood, put it right onto this tool, and within minutes to an hour or so, you'll be able to give those same results without having to store and ship that blood samples down to the ground for analysis. So that will help us as we work on long duration missions such as Gateway, Artemis, Moon, and so forth. Bottom left is another robotics mission. It's another one from our Canadian friends called DDVS, Dexter Deployable Vision System. What it attempts to do is twofold. It attempts to do laser guidance relative navigation for incoming and outgoing vehicles. So this will help CSA, the Canadian Space Agency, work on technology for future missions that they might have. It also has a capability to detailed focused inspection, kind of like we did with the shuttles and the tiles, and for damage, making sure it was safe to return. This system will be able to do focused inspection of vehicles in the ISS to make sure there's no damage, and if there's damage, to assess and to tell so we can capture the risk associated with that. Then the top middle is the alpha magnetic spectrometer. Another fun one is the international collaboration across literally the entire globe. This is looking for dark matter and antimatter in the universe, the origins of the universe. And it's been able to find and put together or collect the largest amount of antimatter ever seen. It's finding glimpses of dark matter in the universe. The next one down is the biomonitor. This will be able to help us real time figure out how the crew's doing without just asking for blood samples and verbally saying. We'll have a physical vest, or in the future a shirt that has electrodes and is able to capture and downlink the crew's vital signs to our flight surgeons, so we can assess and better give advice on how they can do countermeasures. The bottom one is there's a hard view. It's hard to see there, but it's called a slingshot. It attaches to the front end of the Cygnus vehicle, and it's able to deploy CubeSats into space. CubeSats are huge right now. They're able to use small volume, deploy satellites or constellations of satellites into space, and accomplish lots of different technology demos, STEM missions, and also a lot of government demonstrations, along with private industry demonstrations. Back up top is that One Strange Rock. We've sent up one of the earliest virtual reality cameras to space. Didn't end up being much virtual reality, but it was a 360-degree camera. And the footage was used for the National Geographic 10-episode One Strange Rock series, which was really cool. Below that is one of the astronauts taking EKG, sorry, not EKG, but ultrasound, sorry, verbose here, ultrasound of his parts of his body, and that's part of the vascular echo investigation. That investigation wants to characterize how our blood vessels change in space, long duration space. And the preliminary results show that your internal organs tend to seemingly age quicker in space. And so if they can characterize and figure out why and how it's happening, we can figure out countermeasures to prevent it in the future. The bottom one, where the astronaut's wearing goggles, is another CSA one called Vection. it tests and tries to analyze the astronaut's perception in space. In space, the crew doesn't have gravity, so their eardrums and their whole sense of up, down, left, right is all out of whack. Also, their sense of spatial distance, front to back, left to right, is a little bit out of whack too. And so this actually uses virtual reality games to measure the disparity between actual and what the crew perceives. So we can try to work on countermeasures to get them back to reality, per se. Upper right-hand corner is another STEM investigation called Tomato Sphere. It flies tomato plant seeds up into space, and it brings them back down to elementary and middle school classes so they can grow the space seeds and compare them to the control seeds that never went into space. See if there's any differences in those aspects of things. Right underneath that is a really cool piece of hardware which called a Z-Cam, and that investigation is called the ISS Experience. That's one that I'm working on heavily right now. It's basically gonna do 360-degree virtual reality 4K footage in 4 episodes, and I'll go to planetariums and international roadshow over the next year to 18 months, documenting the ISS, all it does, and hopefully, cross your fingers, they're going to take a version of this outside on a spacewalk in either late this year or early next year, so we all can experience what it really is like to be an astronaut, both in space, doing internal work, and going out on a spacewalk. Imagine those views that you can turn around and be in charge of looking at the ISS, looking at stars out in the sky, looking down at Earth. It'd be really, really cool experience. Underneath that is a investigation called FURFY, and that's an investigation that looks to figure out how to do refueling operations in space, to refuel satellites that have depleted all its fuel resources. So it has 2 pieces of hardware and a tube in between, and it works on transferring the water from one to another and the sloshing around, and how do you measure how much is in one tank versus another if you don't have gravity to keep the liquids in a certain area if it's constantly sloshing. And finally, the bottom right-hand corner is a supercomputer from Hewlett-Packard called Spaceborne Computer. It takes the latest COTS equipment and sees if they can figure out ways to make it run without having super expensive equipment, and it uses different ways to harden the software against radiation hits in space. So it's basically supercomputing on a dime with the latest equipment, COTS. So I know that was a mouthful, but I wanted to talk about all the different research. And the next slide, if you go to the next slide, has more. I'm not going to spend a lot of time on this, but there's been tons of experiments to date in biology, biotech, earth space, physical science, human research, even fully commercial endeavors now that showcase what microgravity can do for us and provides a benefit for us on the Earth. So the different aspects could be either NASA research, national lab research, international research, education, a whole bunch of different platforms. Next slide, please. And this is more examples of space station science, ultrasound, purification, cancer treatment drugs, Parkinson research is being going on right now, vaccine development, nutrition studies, bone loss studies, just tons of aspects. And something that you don't see a lot of or don't hear a lot of is imagery taken by the crew and by the assets outside of the ISS looking down, helps us monitor climate change, natural disaster recovery, and so forth. That helps benefit the Earth. Next slide, please. And then finally, a robotic surgery. For the robotics team here, the Space Shuttle Neiss robotics technology has led to the first MRI compatible. They're doing assisted procedures and robotically controlled hardware from the ground on the crew there's a lot of different aspects of remote manipulation or remote guidance that the ISS is being used as a test bed for. So it's really cool, and this also helps in disaster areas where the doctors can't be there. That they can help someone work that isn't very adept at things. They can talk things through, or even remote guidance the hardware if it's there, and help the person that needs it in the disaster area. Next slide, please. Okay, so this is just some benefits, or a little bit of the trips I've been able to go on. I don't know if you could see the title, but it says National and International Travel Opportunities. So NASA has partners with tons of different space agencies, and we have a lot of different centers in the U.S. So some of the different trips I've been able to go on for work and be able to work with those various partners is France, or their ESA colleagues. I've been to DC a couple times for headquarters. The San Francisco Mountain View area where Ames is. The bottom one is Maui. Yes, we have a payload that is on Maui, Mobile Space Lab. They work on types of microscopy, in high cutting edge microscopy in space. The middle one with the cathedral is Montreal, with our CSA headquarters there. Los Angeles for our trips to visit our partner SpaceX. Been to Germany to work on the AMS collaboration project, Aachen. Phoenix is where our Boeing counterparts work on the computer systems, where they develop the computer hardware that talks to all the different parts of the space station. Huntsville, Alabama is a big piece. It's a center of payload operations. I've been there many times. So just, if you work in the aerospace industry or a lot of engineering industry, you'll get to travel to a lot of different places and see the different aspects of the industry you're in. Next slide, please. So talked a lot about that. And so briefly, I'll try to keep this brief, but wanted to hit on the next major projects and programs that JSC and NASA is working on. They're the Artemis, the Gateway moon landing project. So you see in this slide that we're working on future capabilities to get us to the moon. And this is just a snapshot of all the different steps we think we need to do in what order so we can get boots on the moon in 2024 or as soon as possible. So we need to get landers, we need to get the first humans to the moon around the 2022 area, where they won't land on the moon, but they'll orbit. We need to make sure we get the propulsion system, the descent down, and we have an area for them to habitate as they go around the moon, because we don't want to just go there and come right back. We want to, next time we go, we want to have a permanent presence, if at all possible. So this just shows a snapshot of how we plan to get there. And the next slide shows us more the development of the suits on how to get there and where we're going. And we're going to go to the South Pole. That's where we want to go. That's what we've been dictated to do. We're going to try to get boots on the moon for the next man and the first woman on the South Pole of the moon, because we believe there's water there. Actually, we know there's water there. So that'll be one of the resources that helps keep us there permanently. And so this showcases we need our partners' help to get there. We're not going to do this all just with the US. We need our international partners and the collaboration to help make the hardware and build the coalition to do it, and do it safely, and do it in an expedient fashion. So why the moon? So we can do the test bed on Mars. Next slide, please. So we need to demonstrate how we're gonna get to Mars. And the obvious way of doing it is having a permanent base on the moon, showcasing how we can live and work on the moon, how we can, make most of the resources there, and showcase, and find answers to the problems that we're gonna come find at Mars. Next slide, please. that copy. So I think next slide, there might be a copy. Yes. So there's just another cool hyperlink to want to spot the station. I don't know if you've ever tried to see the space station fly overhead. It's really cool. And yes, you can see it with the naked eye. It's the brightest star in the sky, and it goes by quickly. If the lighting conditions are perfect, you can even see the edges of the solar rays in the sky. And sometimes when you have visiting vehicles coming and going, you can see that vehicle trying to catch up to the space station. So it's a really cool resource. I know in the Pittsburgh area, my family's been able to see it in the sky. So I want to put that out there. And next slide, please. And the last bit I wanted to talk about before I take questions is I talked a lot about the work aspect of things. When you get to work, that you work hard. NASA works really hard. But the cool thing about Johnson Space Center and the various other centers is that, especially in the younger crowds, there is a very large social network. When you work in mission control, since you work the hours you work on, you're working overnights, you're working simulations for 10, 12 hours sometimes, your coworkers become your family, especially if you're a transplant like me. And there's a lot of transplants that aren't native Texans that come to the Houston area. So your work family becomes your family. And this just shows some aspects of what NASA has here. It has its own recreational programs, has recreational soccer, softball, kickball, and then some areas that I got to do was when I was down here, as you saw in the Penn State slides, I was in the marching band. I got to network through NASA with the Houston Dynamo soccer team in their first year down here. And I got to be part of their pep band, and they took us to their championship. They ended up winning the championship the first 2 years. It was a lot of fun going with them. We gave tours to the Philadelphia Phillies and various other teams when they come down here. And one of the benefits was the radio broadcasting team invited my friend and I to a game, and we got to go be guest broadcasters during the Philadelphia Phillies game for a couple innings. So that's me in there in the booth broadcasting when the Phillies were playing the Astros. And then, as I said, the work family becomes your family. That's a picture of my coworkers at a wedding. As you can see, we're all come from various backgrounds, various nationalities. One piece of advice is that you want the diverse opinions and diverse cultures in your workforce. You should welcome it. It makes a better team, and it opens your eyes on various options available when problems hit that you might not be thinking of, and you come to better solutions. So I just wanted to put that out there while I could there. And I think that might be the last slide before we take questions. Yes, it is.
All right, thank you. That's wonderful. We can start on the questions now. So, all right, first question. Let's see here. What would be your best recommendation for kids who are seriously interested in a future career with NASA?
That's a good question. First, both astronauts and just normal NASA engineers or various aspects of NASA, finance, business, direct science, research. Be passionate in what you do. We hear it a lot here, and that's really when I do interviews for new hires. That's what we're looking for. We're looking for passion. One way you can do that is, as part of the robotics team. That shows you're above and beyond. You really love what you do. But that's the one key thing I say: be passionate in what you do. Career choices and focus choices, it matters a little bit. If you're engineering, be passionate, but get your math and sciences down. Work a breadth of knowledge, and then you don't have to be the top of your class. The very 4.0, 5.0, you don't have to be that. You have to be good at what you do. You have to be a good student and a good work ethic. That's really what NASA's looking for. And honestly, NASA has an interesting hiring aspect. If you really wanted to be a civil servant, the best advice I could give is look for internships when you enter your college years. That would be the key to getting your foot in the door as a civil servant. NASA hires tons of contractors. A lot of contractors work in mission control side by side with civil servants. Boeing, Lockheed, SGT, I can name a whole bunch more, Wiley, whole bunch of contractors, and they're always hiring. And if you can make your career at those, they also convert some of those into civil servants as you go. So there's lots of different ways you can get into NASA. But the big thing is be passionate and continue looking for opportunities and showcasing and learning. NASA, you always have to learn new things. As you change roles, you have to start from scratch sometimes. But as you learn, you build up your personality traits, and you build up your core soft skills. And that's really what makes a difference when you go through interviews and do your internships. Showcase your soft skills. And I rambled a little bit, but yeah, I think that's a lot of what you're looking for there.
Thank you. All right, next question. What has been your favorite moment in your work and the most stressful moment?
Ooh, okay. Favorite moment, it just varies in time. One of the favorite moments was getting certified, doing my final simulation before I was able to work in the front room. And it was an 11-hour simulation. It was painful. And then waiting an hour to do debrief, and only after debrief you find out you passed. But once you get that, just a weight is lifted off of you. And then working that first week in mission control where you're in charge, you're sending commands 220 miles up into space, you're controlling the cameras up in space, you can look, point it wherever you want or wherever you need to point it. It's a really cool feeling the first time. Working with the shuttle was a really cool time frame. But moving and leading aspects, working with the commercial partners, working with our international partners. There's various moments in history, and my time at NASA just very fulfilling. And research integration is the same. Seeing my payloads get certified, go up in space, and be successful up in space. There's a flip side of that is both in mission control and in payloads when things don't go your way. And my background is we sim a whole lot. So we sim any failure you can pretty much think of. And so that prepared me and give advice to everyone here is that my mission control background has shown me you create a nominal plan, and that's well and good. You pot that out, but you got to have some backup plans. You got to have some contingency plans. You might not need to, have every little line item of what you do in the backup plan, but you need a framework. Contingency is what we call it. So we're always planning what's the contingency. What happens if this fails? How much redundancy is in the plan? So the issues with when I was on console is sometimes you didn't have redundancy. Sometimes you didn't have automatic failover. Sometimes, for me, if something goes really bad, everyone loses communication. And that's happened where we lost communication with the whole space station. Ended up being for hours. Is this something I did? No. It's hardware fails on orbit. And so trying to piece together your knowledge and your experience and explain the various options that could be happening in the dark to your team members when you have people on your back, people's lives at stake. It's stressful, but it's also rewarding because you learn to keep cool under pressure. And when you learn that, the understanding that you don't have all the information, but you can make some educated guesses based on what you do know, how you knew the software and the hardware is going to operate. And then being able to explain that is key as well. So, and in payloads as well, things don't always go your way. And when payloads go wrong, depending on how they were built, they might not get a second chance. So the risk is even higher for those. You have people working a lot of their lives on one payload, like the AMS payload. It needed a series of 3 or 4 spacewalks to fix it early last year, or early this year, I should say. And so that in itself was very hectic because the crew spent years training for this thing that would never, ever plan to be fixed in space, kind of like the Hubble Space Telescope. And anything could go wrong. And you just plan your best and you prepare as best as you can. And you go methodically and hope for the best. And they did have a contingency arise. And the team had some contingency and secondary contingency, third contingency. They went all the way down to a cuff checklist, or a checklist on someone's desk that ended up having a framework of how to work this problem that they never thought could be possible, but ended up coming into play. And so those are the stressful times, but they're also rewarding knowing that you've prepared as best as you can. And sometimes there are times in NASA where even the best preparation won't be able to fix things. And that you just have to understand and make sure you're making the best decision you can with the best information available. And sometimes the best decision is not a decision. Sometimes it's to wait for more information to come to play. So.
I see. So some more specific questions. What are some of the benefits of conducting research on a space station opposed to an Earth lab? What kinds of unique things can be done there? Any other benefits opposed to just reduced gravity?
There's lots of benefits. It's a test bed for technology demonstration, for remote work, and for one of the things that we do for technology demonstration is to do a time differential of commanding and the onboard systems getting those commands. So we could simulate delays in the telemetry and the commands and the voice, and working with crew that we could simulate moon missions or Mars missions. So that's one of the added benefits of going to space. Microgravity is the key, though. A lot of stuff you do in microgravity you can only do in the space station right now. It's a continual source. It's a long duration microgravity. Things like cancer research, protein growth. So why we say cancer research and human research, why is microgravity such a big issue or a big benefit of that? Well, we've noticed in microgravity that the aging processes and the internal body processes are sped up a little bit. So we could simulate, depending on how you set things up, things that are seen in elderly, things that are seen in patients that are at rest on the ground, that are stuck in hospital beds for a long duration. We can accelerate cancer growth in space, so we can come up with various ways to attack and remedy that. Same with Parkinson's research. All those viruses or not viruses, but the genetic and internal body research can be done quicker in space, and we can test a variety of things using those controls in space compared to the ground. So that's one aspect. Technology demonstration is really the big one as well, to demonstrate how things work in microgravity and sometimes in the vacuum of space, if we're going to go to the moon, Mars, and also commercial low Earth orbit. That we have a vehicle right now that's constantly orbiting the Earth, goes around every 90 minutes. It's consistently at a certain altitude. We can put things on there that can demonstrate how something would operate at a similar orbit or even higher, and without it losing control or deorbiting, we can test it for long-term testing and run to the ground, meaning run it to and knock out all the different bugs while we have it in space. Also, in space, there's a whole bunch of remote sensing that we can do of the Earth and from outside, or from the orbital platform out into the solar system. You can use some of that. You do some of that with Hubble and James Webb Telescope, but the ISS provides a way to modify and quickly change the orientation of where it's going, what it's pointing to, with minimal negative results. So it's a very vast aspect human research, biological and physical sciences, as along with tech demonstration, and trying to build out the commercial low Earth orbit marketplace for future space. Eventually, we're trying to be where NASA isn't the team that's building all the hardware for space. We're enabling commercial companies to build items for low Earth orbit vehicles and space stations, and we'd be one of many customers to bring down the cost and to enable other people to purchase aspects and do their research in space and build up the economy to lower costs for everyone, including NASA. So that's really one of the main goals that we're trying to do. And ISS is the key to doing all that.
Okay, so the MacGyver-esque position, I believe that was OSO, where they had to fix things. What kind of prerequisites are there for that?
That one is really an engineering background, really. And to have some sort of engineering background, doesn't have to be mechanical, but it's you do engineering background, and then once you are you do interview, they will teach you a lot of things. You will work with the crew, and you will be able to learn the mentalities, learn how to MacGyver things. Obviously, if you have that type of background, if you're a hands-on mechanic type, likes to tinker with things, that's an added plus. But it really is about how you think and approach the problem, and knowing what tools are available, and being able to work as a team member, work with the crew members, work with astronauts, figure out new ways to approach problems. You do not have to be a specialist. You don't have to learn all the tools of the trade on your own or in school. You just have to have the background and the aptitude to learn those things once you come on to NASA.
All right. And about your career, so is this something that you would consider normal, the path you took? Or were there some special opportunities that you found that helped you get to where you are?
One, I got to be honest, I was probably lucky. I know a lot of people strive to work at a place like NASA or other areas like, other government or industry, Google, Facebook. A lot of people are really looking for certain aspects. They think that's the holy grail of opportunities. You have to be lucky, but you have to put yourself in a position to succeed. You have to put yourself out there. So that's the key. Knowing that the answer might be no. It's okay. You have to get comfortable with that. So when I went to career fairs, it took me 5 or 6 years of constantly going to the career fairs and talking to the NASA booth before they speak to me and before I got past the initial cut, per se. So it takes persistence. I know some of my astronaut friends said one of them got accepted the 15th try they submitted for their astronaut application. So it takes persistence. You have to have your background. You have to be go-getter. That's a real good thing. And with NASA, it's getting more and more to being a good team player. You can't do everything on your own. There are very few positions where you can be by yourself and be successful and shut out the rest of the team or the rest of experts. There are some, I don't want to preclude that, but especially in the projects and programs that I've been part of, it takes a whole bunch of team members, and being able to communicate and work well as part of a team, be both the team leader and a team follower, being an assistant, being able to switch roles and being able to work well with others, even if you have differing opinions, is key. So I'd say I took a normal career path. I went to a state university. NASA does look at engineering schools and compares them, but they're looking for, a school that puts out solid candidates. They're not looking for, I just want to put, they're looking for different things, different times, but they go after schools that put out a lot of good engineers. So if you're looking at a mission control type position, then yes, I'd say an engineering field would be the target. But a lot of it is your personality in addition to experience. I'd say work on, math and sciences, make sure your team skills are solid, your soft skills are good, and you'll be able to get an opportunity, and then just make the most of your opportunity.
Yeah, so next question. What are some of the major technological problems your team has solved relating to the International Space Station, or some of the major problems you've overcome?
Being communications, one problem that I remember was, so we got two lengths, S-band and Ku-band length. There are different satellite frequency bands. The S-band link will take down all your command and control and a lot of your voice. And your Ku-band system will take down your high rate telemetry and alternate voice aspects. But that's really, that Ku-band is really what all the payload and science data comes down on, and takes down the crew's internet and ability to link to their families. So I was on console when the Ku-band system failed. And the first aspect is, can we get a system up and running again? We had an alternate system, but there's no automatic failover. So figuring out how to do it, figuring out, should we do it? Was it safe to do it? Getting the information and making a diagnosis is what you work on first. And as I alluded to before, being able to communicate and being able to process the technical problems while having to take time to explain what's going on is tough, because you constantly get interrupted or pinged while you're trying to diagnose a problem by asking, hey, what's happening? What's the latest information? Tell me what you're going to do next, while you're trying to figure it out. So that's hard to overcome, but your background gives you enough information, and your training gives you enough information of what data do I have at my disposal to figure out what this could be. And I figured out it ended up being an automatic acquisition of the forward link. So meaning you weren't getting any data back from the station until the station received the front signal from the ground, and it wasn't locking onto the ground. So I was able to do a test run after convincing the flight director that there was no harm of manually trying to send the return link, the ISS to ground link of Ku-band based on where the satellite was. And it worked. So with that, we deduced that the problem was somewhere with the automatic software that detects the signal from the front, from the ground to the station. And we had to either stay manually pointing or switch over to the other satellite dish. Another satellite dish had some other problems, but we were willing to make that trade. So we worked with the team and scheduled that in a good time of the day to minimize impacts to the rest of the team, and then work the details. And I ended up having to stay an extra shift to explain and work the further troubleshooting plans and diagnose to get as much data as you can before you declare something completely failed, or before you close the book on something. And because as soon as you did that, we'd lose all data on that. As soon as we went over to the other working one, we lose a lot of the insight as to how the one that's having anomalies is working. So that's one of them. I told you we lost overall comm one time, and it's same approach. What are you going to do? In my job right now, it's not really as dire, but it's okay. This payload has failed, or the something unexpected happened while the crew was working. What do you want to tell the team to do? What programmatic directive do you want to give to the real-time team? Now, what are we willing to use the crew time on? Crew time is expensive. So having to go back and ask the crew to do stuff that isn't scheduled is very costly for NASA and for the other payloads and science and investigations that are getting bumped now, because you have to now shove in this new activity. So it's a different aspect, but it's the same mental approach. What's the contingency? What is the risk? What's the cost benefit? And what is your recommendation? One thing is, you'll see as you get into college and the workforce, is you can come up with options, and your managers and the people in charge are going to want to hear your recommendations and why. And guess what? They might overrule you, but they want to hear why you're going for something, And maybe they have more information than you. Maybe they have information you didn't know about, and that's okay. But the object for your position is to make a decision based on the information you have available to you. And sometimes that's right, and sometimes that's wrong.
All right, so we are running out of time, but one last question to wrap things up. Mr. Neiss, what is the best advice you've ever heard?
Well, okay, the best advice I've heard, and I had a version of it when I was growing up, and it really is from, I think it's Michael Jordan, when he was talking about pathways and choices and mentalities. And it's you will miss 100% of the shots you don't take. So my advice is put yourself out there. It can be scary. You could be wrong. You could get rejected. People can say no, but you'll never know until you put yourself in a position where someone else has to say no to you. If you say no to yourself, it's zero chance. And so all through my career and even personal life is you get the mentality of, okay, it's scary, but I'm going to go for it because I'm going to make someone else tell me no. And I heard the same thing from a bunch of astronauts, their career path. Make someone else tell you no. And another thing is a quote here. I know it inverts the words on the screen, but it says, what would you attempt to do if you knew you could not fail? So if you knew you would not fail at anything you tried, what would you do? And just think about that. And think about, okay, if you fail, what's the worst that can happen? So put yourself out there is the key thing. You need to come to comfort with yourself, and you'll do yourself good by putting yourself out there, because you'll get the answer yes sometimes, and that'll make a big difference. I mean, I got rejected 5 times from NASA for various things, reasons I don't even know of. But that 6th time they said yes, and now I'm loving what I do. So just make someone else tell you no.
All right, thank you for that great advice and for joining us today. We'll be sending you a gift bag as a thank you as well. And of course, thank you to everyone for watching. Sorry if we did not get to your question. Mr. Neiss will try to answer those by email. And be sure to tune in next month on September 25th, where we will have Fu Nguyen, a staff engineer at Walt Disney Parks and Resort. This live stream will also be rebroadcast on your local Armstrong neighborhood channel. Thanks for watching, and see you next month.